Okay, great. Hello, everyone. Good morning, good afternoon, or good night, depending on where you're joining us from. So happy to have you here for the second part of our sustainability series. At the last series, I think at the last presentation where Tom gave an overview on sustainability and basically an introduction to structural engineers and what we could be doing in terms of sustainability, we had at least 50 participants, which was excellent. We know that based on the current trajectories that we're facing in terms of climate change and global shifts, that we do need to have more dramatic action if we plan to try to curb or dent the current trajectory. So I'm happy to have you all on board. It's great that we're all part of the sustainability movement. And just to let you very briefly about Tom, for those of you who are attending for the first time, he is a sustainability consultant with the UK Ramboll group and their arm on the UK Sustainability Solution team. I asked him just before everybody logged in what was one of his proudest moments. And I think this is fantastic as well, right? Because Tom is part of a group that has created a business model for clients saving carbon. And this is what we all need to start doing because it all comes down to dollars and cents when you're making decisions in terms of sustainability. So him imparting these ideas and his passion and his knowledge, and he is extremely passionate and knowledgeable about this, given his past 10 years of experience in this field. I'll now pass you over to him, where today he'll go into a bit more details into exactly how we can reduce carbon on our buildings. So Tom, over to you. Oh, just one last housekeeping bit of things. Tom is happy that if anybody has any burning questions during his presentation, that you could unmute yourself and interrupt and ask your questions. Otherwise, you can do so at the end of the presentation. Thank you. Over to you, Tom.
Thanks very much, Leonie. And yeah, feel free just to stick any questions you've got in the chat. And also, if you want to, you can turn your cameras on while I'm presenting, because it's always nice to see people. So see if any of the jokes actually land. Or yeah, but there's no jokes in this one. It's much more serious. So today we're going to be talking about carbon in structures. Yeah, just a bit of background to me. So principal sustainability consultant. I'm the UK Buildings LCA lead for Ramboll. Yeah, chartered structural engineer and part of the IStructE sustainability panel as well. So thank you very much for inviting me here to talk to you guys today. Obviously, my experience is mainly UK based, with a bit of experience in Singapore as well, but hopefully some of the kind of techniques and stuff that we're using and talking about today will be applicable in the Caribbean region as well. So if you didn't catch my first session, that was on sustainable building design, and we talked a bit about sustainable buildings, impact reduction strategies, and ways that you can approach it on projects, and also some examples of good practice. In this session today, we're going to be focusing deeper on carbon in structures. So we're going to talk about basically climate emergency, life cycle assessment as a tool to measure and manage carbon in buildings. Some of the resources the IStructE provided, and we're going to go through a quick kind of worked example as well to show you that it's actually fairly straightforward. And then finally, we'll kind of finish on informing and influencing clients. So basically, how can you use these tools and these techniques to try and change designs effectively and encourage clients to reduce the impacts of their projects. All right, so carbon deep dive. I'm going to have some questions coming up in this. I didn't do any polls or anything. I probably should set this up better, but if you've got any questions or anything, sorry, if you've got any suggestions to answers to these questions, then maybe just stick them in the chat as we go through. So this is our global carbon budget. So as of 1750, if we want to stop the world to warming, from warming to more than 1.5 degrees on average, we have only got 2,750 gigatons of carbon dioxide to spend. And how much have we spent so far? Unfortunately, we've already used 90% of that budget. So we're quite a long way there. The latest IPCC report is pretty damning and says that we're pretty unlikely to get 1.5 degrees now. And the most depressing thing is that I made this slide 3 years ago and I had to chop off 5% and 3 years of remaining life left. So we're not moving fast enough and we need to change what we're doing now. And I hope that's fairly clear and obvious from all the work you've seen and all the press and everything recently. But yeah, this is very much kind of our problem to solve immediately. Our current spend globally is about 42 gigatons a year. So at this rate, we've probably got less than 7 years left. There's a good chance we'll actually pass the 1.5 degrees C warming threshold before 2030, which is obviously not ideal. But buildings are a really key part of this. And actually, you guys have got a lot of influence over this. So in terms of global emissions, buildings contribute about 40% of that. So 28%, that roughly is the operational emissions. So that's actually like running and heating and cooling buildings, using electricity for services, things like that. And then 11% is the embodied emissions. And this is where we have a big influence as structural engineers, because this is basically all the products and emissions that go into manufacturing products and construction materials, basically. So does anyone want to have a guess at what their influence is? So this on, by the way, on the left is your personal influence. So I had a quick look online. I think it kind of depends exactly which Caribbean nation you live in, but it's somewhere between like 2 and 3 tons. Potentially a bit more in Trinidad. I can quite work out why that was. In the UK, it's about 5 tons. Although to be fair, we tend to like export all our emissions, so we don't manufacture products in the UK. We get them from other places, and then yeah, there's a bit of accounting magic there going on. But this is like your kind of personal impact. This is all the food you eat, you know, heating or cooling your home, driving around, getting to work, etc. That's like your kind of personal impact. Does anyone have a guess at what your professional emissions are likely to be in the order of? So this is like the influence that you have over projects. Feel free to set your answers in the chat. I'll give you a clue. It's more than 2.5. No guesses? No one has any idea? Oh, 20 tons? 3.5? All good guesses. Yeah, it's more than that, a bit higher. The answer is about 900. So this is based on a study that we did in the UK of our building structures teams. And it was based on basically the total amount of buildings that we design in a year, divided up equally between each person in the buildings team. So this is your professional influence. It depends exactly how you measure this, but it's going to be orders of magnitude, probably at least 2 orders of magnitude larger than your personal impact. And the upshot of this is that if you can design your buildings to be 1% lower carbon, so you can cut 1% off the footprint of your buildings per year, you've already saved more than if you cut your entire personal carbon footprint. So the biggest impact you're going to have is through your professional career. So how do we actually do that? Well, first of all, we need to know where the carbon is, and that's where life cycle assessment actually comes into it. So life cycle assessment is basically the tool to measure environmental impacts of construction. It's pretty simple, really. We design some buildings. You calculate all your material quantities, and then you multiply those quantities by suitable carbon factors. And then you add it all up. It's just a big accounting exercise, basically, and you get a carbon footprint at the end. And that kind of tells you where the carbon is in the building. It's slightly more complicated than that. And that's kind of the high level principle. You might have seen this before. These are the different life cycle stages. So I've pulled this out of the IStructE guide, how to calculate embodied carbon. I'll talk through each of these in a little bit more detail. So at different stages of the building's life, it has different environmental impacts, and the materials and products that go into the building have different environmental impacts, hence life cycle assessment covers the whole life cycle. There's first of all the product stage, which is your A1 to A3. So this is all the kind of upstream impacts of basically manufacturing the materials. So that's extracting all the raw materials, transporting it to a factory, the manufacturing processes and any kind of energy used, for example, in processing steelwork. There's a lot of energy in the A3 stage. Then you've got to get it out of the factory gate to your site. So that's the A4 transportation stage. And then you've actually got to assemble it and turn it into a building. So that's the kind of A5 construction stage. So this bit, the A stages are basically everything that happens before the building is occupied up to practical completion. That's often referred to as A1 to A5. And this is kind of where you can have the most impact. If you look at across the whole building, it's not just the structural bits, something like half of this like whole life embodied carbon is just in these upfront bits, plus another 5% on transport and construction activities. Then the building's in use, and then over the next 60 years, it's going to be used, it's going to be maintained, repaired. Maybe you need to replace the facade at one point during its life, but you keep the structure. This is kind of more relevant to maybe the architectural and the services bits of it, because most of the time we put a structure in and then we leave it. We don't have to worry about it because we design things to be durable. But that's the B stages. That's all the kind of in-use bits. This red bit down here is the red bordered bit is the operational energy. So this is basically all the energy used to heat and cool the building, run building services, or also plug-in loads and things as well for people actually using the building. So that's the B stages there. And that's referred to as the operational carbon. So that's where those sit in the life cycle assessment stages. And then the embodied carbon is basically everything else in this picture. At the end of the building's life, then we have to demolish the building or deconstruct it, hopefully. We need to transport those materials that come from the demolition activities to some sort of waste processing facility and dispose of them. And that's the C stages here. So that's the up to grave. And then in theory, if you've designed your building using lots of materials that can be easily recycled, or if you've designed a building that could be taken apart and reused somewhere else, like you've got something like modular system, then there's basically a potential to basically reduce the impact of a future project. So maybe you've got a building that can be taken apart and reused as is. That means you don't need to kind of make a new building the second time around. And you can quantify the benefits of doing that in the D stage. So this is basically the impact to the next life cycle, the benefits and loads beyond the system boundary. So that's what that's it. So that's also kind of like a measure of circularity, although not really a very good one, but it gives you a kind of an idea of it. But the vast majority of these carbon emissions are actually in the upfront bit, and that's also where the majority of the structural engineer will have an influence. So when is the carbon emitted? This is like a life cycle of the building. Most of it is going to happen at year zero, i.e. before the building is even built. And around 50% of the building's whole life emissions actually occur before the building is even occupied. So this is before where we can have the most impact. And then these next bits happen over the next 60 years or so. And hopefully, electrical grids will decarbonize, and this will kind of reduce over time anyway. And then with any luck in 60 years time, when this building reaches the end of its service life, there'll be better kind of systems and processes for recovering materials, which also reduce that. So really the main impact we can have now is in this upfront stage. And it's interesting that actually, if you break down that those upfront carbon emissions, the structure is actually the majority of those upfront emissions. So this is an internal project database that we've got, and we've kind of taken an average of about 50 different projects here. And this is not just looking at structures, it's looking holistically across the whole building. And of your upfront emissions, the structure is more than 50% of those initial upfront emissions. So the question is, where is it in the structure? And again, this varies quite a lot. So it could be in the substructure. If you've got like a large basement, for example, then basements are very high intensity. It could be in the structural frame. It could be in the floor slab, and usually the floor slabs are quite significant. It could be in the roofs. It could be in the stairs and ramps. But actually, this just shows that there's a huge amount of variability in projects. So trying to draw a kind of consistent benchmark and say, oh, every project needs to be less than 300 or whatever the number you pick, it's quite difficult because actually there's just so much variation anyway. It's very kind of project specific. So I think we had a question about targets last week, and this just shows you like how hard it is to actually draw a kind of realistic target. It's worth noting that some of these ones, basically all the ones down the end here, these small impacts are all just refurbishment projects. So maybe there's very little in the way of structural change going on, and therefore the impacts are quite low. So what materials actually are contributing to that carbon? Well, it's certainly in our project database. The majority of it is the concrete, ready-mix concrete, either regular strength or high strength. It's the reinforcement that's going into the rebar. It's structural steel and steel profiles. And then it's site operations as well. So this is basically excavation works, piling rigs driving around, energy and fuel use on site. This is the A5 bit of your construction. But these kind of key structural materials are a really big impact. There's a bit of CLT and some other timber stuff in here, but that just shows you how kind of uncommon timber construction is still in the UK. That our selection of 50 projects doesn't necessarily include that much. Great, so now let's talk about material impacts. So we kind of understand where the carbon is and what the different life cycle stages are and basically how to account for it. We've got another challenge for you, which we'll see if this works. It seems like it's a slow lunchtime for everyone. But we've got a few carbon factors on screen. So these are kilos of carbon dioxide per kilo of material used in the building. We've got some very high intensity materials here. So these ones up here, and there's also relatively low intensity materials down here, or some sort of averaging ones. Not quite sure how I'm going to do this pop quiz, but there's a few different materials. We've got the steel, concrete, timber, insulation, and plasterboard, the 5 options here. So maybe just have a think about which one you think are going to be the highest intensity ones out of those. Which ones do you think are going to be the lowest intensity? Maybe I won't do like answers in the chat because you'd have to cover all of them, but just give the answer. So maybe expect, for example, that concrete might be really high intensity because you've heard that it's really bad. These are your different options. And you can see that actually rock wool, so this is your insulation, per kilo is almost as bad as steel. concrete is actually the lowest out of all of these. Concrete has the lowest carbon footprint per kilo of concrete used. And that's the key thing. This is just the material impact. This is just the carbon factor bit. You've got to think about the quantities as well. Because quantities times carbon factor gives you the total impact. So if you just look at these factors on their own, then you're going to get a skewed picture, because one kilo of concrete is not functionally equivalent to a kilo of steel. We use them in very different applications. So actually maybe a better measure is to actually look at how they're used in the building. So if we instead take an average over a typical floor plate, like per meter squared of floor that we've created with this building, then maybe it'll look something a bit more like this. So your concrete and steel are probably up there on par with each other as kind of highest impacts. Maybe your CLT is a bit more efficient because you maybe need more CLT, but it's quite low impact compared to your steel. And then rock wool and plasterboards, there's not a lot of them going in by mass compared to structural materials. So despite rock wool being very high impact, it's actually quite low carbon overall. And also very light, so it's hardly any weight. So yeah, so the carbon factors themselves don't really matter that much. It's actually how you use it in the project is kind of the important bit. So here we go. We've got 4 more answers for you. Which of these do we think has got the lowest embodied carbon impacts? We've got some carbon rates here. These are kilos of carbon dioxide per meter squared of floor area created. And we've got 4 different structural schemes here for a 9x6 meter grid. So we've got a flat slab RC frame with 290 mm structural depth. We've got a composite steel frame and metal deck. We've got steel beams and columns with an LVL slab. So this is laminated veneer lumber, quite an efficient timber system, but then with more steel. And then we've got a glue lam and CLT system. So maybe just stick your answer in the chat. Which one of these do you think has got the lowest carbon impact? 1, 2, 3, or 4? I'll give you a minute for that.
My vote is 4.
Going for 4. Okay. 4. A few more 4s.
I'm 4.
Someone said 1. Controversial. 3. All right. I'll give you the answer. It's actually 3. So your steel beams and LVL slab, in this analysis at least, tend to be the lowest carbon impact. And that's because your LVL slab, it's very efficient in its use of timber. It's like a cassette system. So you're putting the material in the flanges. You're using timber, which is already kind of low impact, and you've got much less volume. So if you use a CLT slab, then basically all the material in the middle is kind of wasted. It's not really doing anything structurally. Whereas an LVL slab, because you're making a cassette, you're doing your slab incredibly efficiently. And the majority of the structural embodied carbon is usually in the slab. So basically, if you get your slabs and your beams right, then everything else just kind of works anyway. So it kind of points you towards picking the right floor structure more than anything else. And actually, there's a little bit of steel in here, but because we've kind of mixed, we've used steel in the most appropriate place, and then used glue lam beams everywhere else to kind of tie things and use timber for the floors, then it kind of works quite well. Your composite steel frame and metal deck is the highest, and that's mainly because the profiled metal deck that we're using to support the concrete is very high intensity. You've got a lot of steel in there, basically, like per meter squared of floor. So they're making basically a whole sheet of steel across the whole floor plate, and then also some concrete on top of that and rebar potentially. And your flat slab RC frame is fairly efficient, although of course this is not very circular. So when you demolish this building, you can't really do anything other than crush it down to aggregate. Whereas in theory, your steel and your CLT could potentially be reused a bit more. So worth thinking about that as well, not focusing too much on the carbon. But yeah, maybe a slightly surprising result there. Okay, so how have I actually come out with working these carbon footprints out? So the IStructE here, I've got this guide called How to Calculate Embodied Carbon, which hopefully you guys have seen before. Just gonna grab a drink. I'm going to talk you through a kind of worked example. You don't have to go along with this because it's a bit of maths involved, and it seems like everyone's eating their lunch anyway. So, but here I'm going to talk you through basically how we calculate the carbon impact of, say, a typical concrete flat slab. So in this example, we've got a 9 by 9 meter concrete frame on a structural grid. It's 350 thick slab. It's a C3240 concrete mix with 100 kilos per meter cubed of reinforcement in that concrete. And this is part of a wider 4-story office. So 15 million pounds construction cost. There's £1 million in the UK. Don't quite know what the conversions are. So basically the process here and the guide How to Calculate Embodied Carbon talks you through this in a lot of detail. So you can go back and refer to that later. But basically what we want to do is work out all the material volumes and weights, first of all, then select some suitable carbon factors, which the guide gives you. Then you calculate your A1 to A3 carbon per meter squared of floor. So that's the upfront carbon emissions from manufacturing the materials. Then we work out our transportation emissions, so how much carbon is expended getting all this concrete to site and reinforcement. And then how much is part of the A5 emissions, so the waste that is generated on site, and also emissions from site operations and driving diggers around and whatever. So just run through it then. So work out material volumes and weights. Hopefully you can all do this. Slab thickness times your 9x9 grid gives you 28 meters cubed of concrete. We've got 100 kilos per meter cubed of rebar, multiplied by that volume, and we get about 2.8 tons of rebar. And then in terms of the weight of that concrete, I've taken 2450 as my density. So we've got about 69 tons of concrete. So we've got a kilos of materials. So we've got the quantities. So now we need to multiply those by some carbon factors. So I've pulled out this table from the IStructE guide. They give a few different examples of different concretes. They give some examples of different strength grades in the UK, first of all, which is quite useful to see anyway, because fundamentally, if you've got less cement in the building, which you will have for lower strength concretes, then you will have lower carbon factors. But they've also included this global average, which I thought was probably most appropriate if we're talking about buildings in the Caribbean. I did have a little bit of a dig to see if I could find EPDs and kind of better carbon data for that region, but I couldn't really couldn't find anything in like the one-click database. And I don't know if that's just because you don't do much in terms of kind of concrete and steel production on the islands, and is it like mainly imported from the US, or yeah, I'm not sure. I'm not too familiar.
Concrete is manufactured across 3 countries: Barbados, Jamaica, and Trinidad.
Okay.
The other smaller islands would have gotten imports from those countries. But perhaps the manufacturers, which is a Mexican company, I believe, CMEX, maybe they don't publish carbon data, so that could be why.
Okay, yeah, that's good to know. So what you probably the best way to do it then would be to look up the CMEX EPDs, because maybe they'd have a kind of general regional one, and they might publish it on their website, for example. So if you wanted to get like a slightly more accurate picture rather than just this general one, then that might be a good starting point. But anyway, so we have to pick a suitable carbon factor, and we can see it's already quite complicated to get this. So, but hopefully this will give you a steer on kind of the right sort of order of magnitude at least. And then we've picked global average for reinforcement as well. Now, steel varies quite a lot in terms of its carbon factors, and it basically depends on the amount of recycled content in it, and whether it's using the electric arc furnace process production route, or whether it's using the basic oxygen furnace. So the kind of blast furnace, basic oxygen furnace approach uses coal basically to fuel it, which is a fossil fuel, and obviously has very high emissions. And also you normally have a maximum of about 20% recycled content in that sort of steel. So high grade products like metal decks, for example, they're likely to be manufactured using that process. Whereas lower grade products like rebar, which is generally just like the kind of worst of the worst when it comes to from a steel manufacturing point of view, that can be manufactured using the electric arc furnace a bit more easily. But it very much depends on whether or not you've got the production system set up for that locally. But the electric arc furnace using 96% recycled content could have a carbon factor as low as like 0.4. And then actually most UK produced steel uses quite high recycled content. So we have a lower carbon factor here. If you're using all virgin materials and no recycled content, then it could be up to something like 4 even potentially. So there's a big range here, but let's take a number in the middle. We'll take 2 for this exercise. So we've got our carbon factors. Now we do carbon factors times quantities. So 2.8 tons of rebar times our carbon factor of 2 gives us about 5.5 tons or 5,500 kilos of carbon dioxide for the rebar that's gone into this bit of slab. And similarly for the concrete, times our 0.175, we've got about 12 tons of carbon dioxide. So that adds up for this 9x9 bay to be 17.7 tons or 17,700 kilos. But then we want to prorata this down to a per meter squared GIA. So, if you've just got a big number, 17 tons or whatever, it's kind of meaningless without knowing how big the building is. So in order to compare buildings like for like, we always want to kind of bring it back down to a per meter squared rate, so we can compare large buildings and small buildings and get more of a feel for how these numbers will work and what they mean. So that then boils down to 219 kg of CO2 per meter squared. I think I got my maths right, but shout if I've done something wrong here. So that's the upfront emissions. So really quite high if you're familiar with carbon factors, but we'll come back to that later. Now we're going to work out the transportation emissions. So that's the A4 bit. So again, the IStructE guide has got some really useful kind of carbon rates for it, and it tells you how all these are calculated, but it's basically worked out per ton kilometer based on the different transportation methods. And you see that actually sea transport emissions are very low. So per ton of material per kilometer taken by sea, it's like an order of magnitude less than if you took it by road. So sea transport, very efficient method of transportation, at least in carbon terms. And if you're flying stuff around the globe, then it's like 6 times worse than driving it per ton, which is maybe not too surprising. So avoid flying things in and get them by sea instead. So the concrete I've assumed is manufactured locally, so sounds like I got that right. But then the rebar I've assumed that it's come by sea, so I've just said it's kind of global manufacturing. I've just used the kind of default transportation distances of 50 by road and 200 for global manufacture with 10,000 by sea, and that gives you some rates per kilo of carbon dioxide per kilo transported. So it all adds up to basically this being another carbon factor. And then we multiply our total weight of concrete by that first carbon factor, which is the local transportation one, so quite low. And we get 347. So there's a lot of concrete, but it's a very short travel distance potentially. So that ends up being about 350. And then the rebar, there's much less rebar, but it's come much further. So then those two kind of balance out. And then when you divide again by the total area, you get 11 kilos of carbon per meter squared. So 11 compared to 219. Transportation not that significant, it seems, in this case. But obviously that depends very much on your input assumptions and everything, of course. So pick ones that are relevant to your project. And then we're going to talk about the waste as well. When you make concrete on site and pour it, then potentially there's going to be some wastage, and same with rebar, maybe these moth cuts and things like that. The IStructE guide gives you some examples of waste rates. So concrete, they think is about 5%, and rebar about 5% as well. It gets a little bit more complicated to work out. I won't go through all the details, but basically you have to account for the fact that you've had to make a bit too much concrete in this case. You've had to make an extra 5%, so there's some carbon associated with that. And now you've also got to take that waste off site during the construction process and dispose of it somewhere. So you've got some like end of life emissions, but during the construction phase. So the C stage calculations kind of crop up again in A5 because you have to account for the fact that you've overproduced and then also had to take that material away and get rid of it. And there's emissions associated with that. I won't go through it in too much detail, but basically there's a method for doing that. And it works out about 13 kilos of carbon dioxide per meter squared in this case. So that's the waste bit. And then finally, there's the site bit as well. So this is the actual, this is driving a concrete lorry around or a piling rig or whatever, putting up your formwork, setting up all the site and doing all the prelims and everything else. This is quite difficult to measure unless you've actually got data on fuel and energy use on site and water use and things like that. Generally, there's some kind of rates given in the IStructE guide as well and RICS, so they'll just give you like a kind of a starting point again. And if you work through these, I mean, it's questionable how relevant it would be for construction sites in the Caribbean, because these are all based on basically production sites or construction sites in London. But it's maybe like in the right order of magnitude, perhaps. But very welcome to be challenged on this, and if anyone's got better data, that'd be really interesting to hear, so feel free to share that. But that works out about 21 anyway, using these kind of default rates and stuff. So summary then for our 350 mil flat slab RC bay, we've got quite a lot of concrete emission from manufacturing it, quite a lot of rebar, not very much from the transportation, reasonable amount from the waste, and a reasonable amount from the site as well. So it all adds up to about 264 kilos of carbon dioxide per meter squared. And remember, this is just the slab. So all we've done is measure the slab. We haven't included columns, core walls, foundations, all the other bits as well. So like per meter squared of that bit of slab, it's that much. But you need to kind of do this again for the rest of the building, basically quantify everything and work it all out. And then that will give you the actual carbon rate that you can report. But we don't stop here, obviously. We just want to do, this is just a number, and the number's kind of meaningless unless you're going to use it for something and take some action. So here I've looked at what if we did a 25 mil thinner slab, and we could see that that cuts 7% off. So that's quite a good benefit. And what if we change the concrete to something like 25% GGBS? That's a much more significant reduction, actually, 14%. Although obviously noting the things that I raised last time with specification, you can't just spec 100% GGBS and think you're done. You need to still do the reduction first, and then the GGBS and cement replacement, the specifications last. So it seemed quite long-winded, but hopefully not too complicated in principle. And the guide does go into a lot of detail on how to do it. So it's fairly straightforward to follow. But fortunately, there's a tool which does all this for you. So if you want to save yourself a bit of time, you can just download the Structural Carbon tool version 2, which came out March last year. Doesn't quite sound right. I think it's more recent than that. But anyway, this version 2 of the tool is out, and it does all this for you basically. And it's free. So it looks something like this. Here I've plugged in that first calculation that we did. So I've picked, we can't really see this. Let me zoom in a bit. So I've picked my material, I've picked the material type, I've picked the material specification, and given it a location as well. So it can also break it down and tell you like, oh, most of your carbon is in your slab or your columns or whatever. Put in a description, some volumes. These numbers don't match because I was trying to work it out for a whole building. But hopefully you still get the idea that you just put in a material quantity here and then some reinforcement quantities here, and it basically works it all out for you. And as a bonus, it even does the B4 C stage and D stage calculations for you. So you get those for free. So it's a similar principle again. There's some carbon factors you multiply your quantities by, and then it all gets spat out at the end. So based on this, if our building was just a slab everywhere and was somehow floating in the air with no columns and didn't have any substructure, we'd be getting a scores rating of D, which is not great, gonna be honest. Really, D is kind of the target, I think, for most buildings that we're designing today, and we need to obviously get better and better over time. So there's not much budget left in this particular building for everything else that needs to go into the structure. But it gives you a starting point, and it gives you an idea of at least how to work it out, and then you can start making changes based on this, like perhaps tightening up your grid so you can make your slab thinner. All right, so that's how we calculate all of this. Now I'm going to talk a bit about informing and influencing. So how do we actually use these results to try and influence clients and change designs and make an impact? So I think the key thing to remember is that life cycle assessment is always a tool to make informed design changes. We don't want to be measuring it, just getting a number and saying, okay, great, move on. We need to actually use this as a starting point and use this data of, it looks like all the carbon is in the slabs. What can we do about that, for example? These are just a couple of examples that we've, like presentations that we've used for clients before. So here we looked at the option of, this is a whole building life cycle assessment, and we looked at the impact of changing from an in-situ slab to a post-tension slab. It's 15% savings in the overall embodied carbon, but actually for the structure alone, you can save like 50% by doing this on this particular project. So PT seemed like quite a good solution there. And here we kind of looked at like a pathway for a project to get down to their carbon goal. So they had quite a high starting point at that early stage in the design, but then we looked at potential moves that design team could make. Some of them structurals, again, PT slabs, GGBS, those sorts of things, and trying to get them down towards their kind of aspiration and make some savings there. The key way to do this, of course, is to apply that hierarchy of carbon reduction. So remember this from last time, just use less stuff, top of the hierarchy, and then specify low carbon and offset at the end. But really, we need to be going right back to the start and challenging the brief. Do we need to build anything at all? Can we get away with refurbishing an existing building? Can we optimize and make this more efficient and so forth? Ways to then report that to the client. I think there's no reason why we shouldn't be reporting carbon with our scheme design options just as standard. Here's an example in a couple of projects, or a project in Manchester, which is an office development. And the client was interested in a few different ways of framing this building. They wanted to compare steel to concrete. So as part of that, we used the IStructE tool to do a very simple embodied carbon calculation. So we're putting this in front of the client's face and saying, look, these are the impacts of your decisions. These are the things that we can do to optimize this. And I think engineers like having a number as well. Like we like having a figure that we can kind of target and try and improve against and everything. And really, this is kind of one of the first times I think ever in the kind of structural engineering industry, that we have like a thing that we can optimize for, which is actually kind of doing good for the planet. So. And another thing that really is very valuable is actually showing comparisons to similar projects. So again, these numbers are kind of meaningless to most people. You just go, okay, 300 kilos of carbon per meter squared, what does that mean? But if you show them comparisons and say, okay, well, you're designing this hospital. Here's 3 other hospitals we've worked on recently. They've all got a much lower carbon footprint. Why do we think that is? Then suddenly people will sit up and, I put this up in a meeting, and suddenly everyone was really interested. Like, what have we done wrong here? What can we do differently? Why are these projects better? These office comparisons, we then added those in as well to see, like, is it just hospitals that are lower, or are offices generally higher as well? So these kind of things really spark debate if you put them against their peers and say, are you doing better or worse? And that helps quite a lot. And really the key thing is to integrate carbon and circularity impacts into all your design team decisions. So this is an opportunity matrix that we developed on a scheme. And for all of these potential changes to the design, we looked at the upfront carbon impact, circularity impact, and then also cost, program, and all the usual other things, quality as well. So it's the 3 things of cost, program, or to cost, time, and quality. There's now like a 4th dimension, which is sustainability, or carbon, I suppose, if you want to kind of narrow it down to just one figure. And that really should be like part of all our kind of decisions going forward, really. And as structural engineers, we're basically in the right place to provide those figures and that value. So back in the previous session, if you were here, I asked what's the most sustainable way to build. We thought, was it replacing old buildings with energy efficient new ones? Was it using more low carbon timber and construction? Was it building nothing? So maybe it could be any of these things. But actually, I think probably the most viable solution we have right now is actually just upgrade and refurbish older buildings. So minimal carbon impact, maximum social benefit, and hopefully some economic viability as well. So ticking all the boxes. So that was all for me. So fairly quick run through for that. Hopefully not too painful, all the maths. But yeah, I'm very happy to take any questions now. We'll have a bit of discussion about this.
That was really quick, Tom. I feel like I could listen to you for another half an hour. I'm pretty sure you have enough data to keep me occupied for another half an hour.
We can watch the recording of the last one then.
That's true. So we're open to questions now, everyone. So please feel free to unmute yourself, turn on your camera. It'd be great to see your faces as well. But no pressure there. So open for questions.
What is GGBS? First question. Yeah, so I see someone's posted a link actually. So GGBS is a type of cement replacement that you can use in concrete mixes. So the idea is that you're taking out the highest carbon bit of a concrete mix, which is the cement, and replacing it with something else that has similar properties or allows the concrete to behave similarly. It stands for ground granulated blast slag, I think. It's basically a byproduct of the steel making industry. So you're using that waste product in your concrete instead and replacing a certain percentage of your cement with that. And because it's a waste product, it generally has a lower carbon footprint than the cement itself. It can have an effect on cure times, so something to be a bit aware of when it comes to kind of temporary works and program and stuff like that. But yeah, it's definitely a good thing to use. However, it isn't quite high demand because everyone wants to build low carbon buildings, and it's kind of the quickest, easiest way of doing it. It's been around since like the 70s or something, so it's all part of the code as well. So like if you specify GGBS in your projects, you're not going beyond most design codes because it's been around for a long time. Whereas some of the more kind of radical zero carbon cement replacements might need testing or verification to get through the regulatory hoops that you need to make sure it's safe.
Okay, there is another question that came in from the chat from Jack. What does the E in the CO2 emission, well, kilograms of carbon dioxide, what does the E represent?
That's a great question. So the E stands for equivalent. And the main reason for this is that carbon dioxide is not the only greenhouse gas that we have to worry about. So there's also methane is probably the main other large impact on climate change. So methane has much higher global warming effects than carbon dioxide, but you can kind of adjust it so that you can basically say, okay, well, instead of saying methane, we'll just say it's like 14 times carbon dioxide equivalent. So you can basically bring everything back to one number, which just basically means global warming potential generally. Carbon dioxide is still the major one, and particularly the one we have to worry about most in construction. But it's just a way of basically turning everything back into carbon dioxide equivalent.
Okay. I see a couple of people have to leave, but I did say thank you. Another question came in: will the steel fabricator know the values to use for rebar in terms of A1 to A3 values based on the amount of recycled use?
So this is kind of like a sort of specification question then. So if you're, are you sort of saying like if I specify a certain amount of recycled content, or?
Yeah, that's exactly what I mean. Yeah.
Yeah.
So you say when you said before, like whether the value is going to be, I think it was like 4 or 0.4. So when I go, straight to the steel fabricator and be like, this is the amount I want to use, because I think that's one of the problems I've had using the IStructE tool is I'm not sure what actual value to use based on what I'm going to use on site.
Yeah, no, it's a great question. So the IStructE tool doesn't give you too many options when it comes to picking different carbon factors, and that's by design, because they don't want people basically just saying, oh, we need the lowest carbon steel on every project, because there isn't enough of it to go around, basically. The main thing that you can look at is you might be able to specify electric arc furnace instead of blast furnace as your steel production process. Yeah, it's potentially a bit tricky, and perhaps a better approach to specification would be to specify a carbon factor instead. So maybe you look at kind of an average carbon factor of, let's say, 2 for your rebar, and say all steel that we use on our project must have a carbon factor of less than 2 kg per kilo, or 2 kg of carbon dioxide per kilo. And then that at least opens the door to other production processes or methods which maybe don't use electric arc furnace, or maybe use like hydrogen or something like that in the future. But it doesn't like limit them to a particular supplier or a particular manufacturer.
That makes sense. Thank you.
No worries.
Okay, another question from Hussein Imami. He asked about, do you consider cradle to grate or cradle to grave for timber in terms of carbon emissions? First part of the question. And the second part is, do you account for biogenic carbon for timber as well?
That is a great question, and I have a whole separate training course on sustainable timber use that covers this in a lot more detail. I won't try and bring up the slides for it now. It's a great point though, because the end of life use of timber is absolutely critical. Basically, when timber, as it grows, it absorbs carbon dioxide from the atmosphere, and then that carbon dioxide is basically locked away in the timber itself. So if you cut down the tree and then hopefully replant it, and another one grows and absorbs more carbon over the next 50 years. That's the kind of the whole approach to sequestration, that you've got this kind of sustainable wood production process where you're locking away carbon in one bit of timber and then allowing another one to regrow in its place and absorb more carbon again. So now effectively you've now got this bit of timber which you're using in your building, and this is like a store of carbon. So there's almost like a kind of a ticking time bomb of carbon that's waiting to be released. If you burn this timber at the end of its life, then all of that carbon dioxide that it absorbed gets re-emitted, and it won't get reabsorbed by the new tree for another 50 years. So that's the kind of the challenge of sequestration, is basically, how do I take care of this timber, make sure it doesn't get re-emitted at the end of its life? And this is where things like designing for disassembly become really important, because if we can enable this timber product that we're putting in our building now to be potentially reused much more easily in the future in another product, then we're giving it a second life or a third life, and we're prolonging this kind of carbon storage timeline. So yes, you do have to consider cradle to grave. And at the moment, the way the industry measures carbon dioxide for timber products is we don't aggregate the sequestration benefit with the embodied carbon impact of producing that timber. So when you cut down your tree, turn it into a product, there's some like emissions from that process, and that's the kind of embodied carbon of the timber. And then there's the sequestration, which is the actual like carbon locked away in the timber itself, the kind of the timber fabric from the growing process. But this one is much larger, so the sequestration is huge. And if you add these two together, then you get like a big negative carbon number. And then the temptation is then to be like, okay, well, it's negative carbon, therefore I just use as much timber as possible, and now I've got a net zero carbon building. But it doesn't work like that, because you're now kind of overusing this finite resource. So you've got to be very careful not to add in the sequestration benefit to the upfront carbon emissions that you work out, and basically just report it separately. So it's almost like sort of separate from the carbon analysis process. It's just like, here's a property of this timber that, by the way, it's storing some carbon, but you shouldn't really use that as like a kind of a benefit to your accounting on your project. And then this is only temporary, so this only lasts until the building is basically demolished and potentially the timber gets burnt or goes into another building life cycle. But either way, you kind of lose the sequestration benefit at the end. So it's a temporary storage thing.
Okay.
So yeah, it's a slightly complicated answer to a complicated problem potentially, but hopefully that's sort of explained it a bit.
Thank you. I actually have two questions. My first question is, you had showed a comparison table, which was fantastic in terms of the carbon between different types of buildings per square meter. Is there a public database that has this information that we can access? In terms of if I had a multi-story office building versus a residential space or hospital, what's the average carbon per square meter that you get based on different building types? And
no. And this is one of the main challenges of the industry at the moment, is that we're not doing very well when it comes to recording and sharing this data in a consistent way. There's starting to be a lot of movement, at least in the UK. There's a new net zero carbon building standard, which is currently being authored, and there's a database behind it as well. And there are some published benchmarks and published guidance, which are based on kind of like limited studies. So I think it was in my, possibly in the further reading. Oh, no, that's a bit. Let me go back up to the previous presentation, because there's a good source in here. So this embodied carbon primer by LETI, which is the London Energy Transformation Initiative. This is UK specific, so may not be that relevant, but it does give some benchmarks for kind of typical carbon footprints of offices, residential buildings, and schools, I think, are the third one. But there's no kind of like consistent industry methodology at the moment for basically like adding stuff into a database and then sharing that all and doing some analysis on it. It's like kind of bits all over the place of different people doing this exercise.
I know the IStructE sustainability panel, perhaps, or maybe at a higher level, it has been discussed a couple of times to see if as part of this movement we could get organizations and companies to share their data that we could then have in some database. But I guess, yeah, we need to do a bit more in that arena. And my last,
getting there.
yeah. Okay, good luck. Keep
slowly,
on it, Tom.
yeah.
And my last question is, in terms of carbon, it's very difficult, especially in the Caribbean, right? I mean, our carbon footprint is fairly low. And you did raise a question as to why it's so high in Trinidad, and it's because of oil and gas. So that's why the GDP carbon per person is so high. So Guyana is going to be up there as well soon. So my question is, what are my easiest wins, for instance, in terms of reducing cost? Because when I'm presenting this to the client, there's no government regulation that tells them their carbon needs to be reduced by a certain amount, right? Maybe large organizations, yes, they try this movement to do it, but generally for private clients and most of the clients who would have in the region, they don't care about carbon. So what they would care about is how can they save a bit of money off of their facility or their building. So I know one is to reduce things like the thickness of your slab. What are the other things that you would approach if that was your challenge? In terms of reducing costs?
Yeah, it's a good question. Actually, this is one of the myths that I presented in the last one, which is that sustainability costs money. I think this is kind of common perception in the industry, but actually a lot of the most sustainable outcomes involve just doing a lot more with less. And if you have less material in your building, then you have lower costs, basically. So if you've got thinner slabs, then less material that needs to be produced, and that saves cost and carbon. So I would focus on the things that come up at the top of this hierarchy around the use less stuff bit. As soon as you get into like specifying low carbon and offsetting, all these things are costing money. Whereas building nothing, building less, building clever, and these kind of approaches to optimizing, taking out basements, removing transfers, reducing grid sizes, reusing existing buildings. All of these things are going to be cheaper because they basically use less stuff and require less resources to be produced, and there'll be significant carbon benefits as well. So if you focus on the bits at the top of the hierarchy, then hopefully you can also demonstrate that there's still social and economic benefits to the client, but maybe with much less environmental damage and much less expenditure upfront.
Okay, all right, great.
Hope that answers.
Do we have any other questions from? I see we have 41 participants left, and we do still have 10
I have a
minutes
question for
left.
Tom.
Yes, Dominic.
Thanks, Tom, again. I have a question about the embodied carbon equivalent number for steel, which the structural tool uses, which doesn't exclude the global number, excludes China, which is interesting because China produces over half of the world's steel. So is that really a global number? I don't see how it can be. So why doesn't, I don't know if you know the answer to this, but why doesn't the IStructE tool, I mean, obviously they state that caveat, but why doesn't it, what's so bad about China?
I don't know the answer to that. I expect it's because of the large amounts of coal and fossil fuels used to produce steel in China, but that would just be a guess. The way to study this properly would be to look at basically EPDs from different countries and look at the assumptions behind them. So an EPD is an environmental products declaration. It's basically like the producer does like a mini LCA looking at all of their products impacts and then publishes the results of that as an A1 to A3 carbon impact. Those sort of EPDs, if you compared some from China to other countries, you might see differences in the production process or the fuel mix used, things like that, which would then explain why the carbon rates are a bit different. As for why it's specifically excluded from the IStructE tool, I don't know, but that'd be a great thing to feedback, so I'm sure we can include it in like the next version potentially. The idea is that we're going to keep kind of updating this and the methodology probably every year, so that it kind of keeps in line with current best practice and gets new data in and everything else. So yeah.
Okay, yeah, I was just curious.
Okay, any questions from anyone else before we close off? Okay, Tom, I'd like to thank you on behalf of everyone. I mean, loads of people in the chat, as they leave, they've been saying thank you and excellent material, and this was really helpful, very informative. And it's been fantastic. I mean, you're a great presenter and you know a lot about this topic. You've been doing a lot, you've been saving a lot of carbon, including that 5,000 tons of carbon in 2022 on your projects, which is it's remarkable, and it's something that we should all aim to do. This has been a fantastic series, and hopefully maybe later in the year or next year, if you're available, we can probably do some presentations on timber. As you say, you have some additional material on that. But on behalf of the Institution of Structural Engineers Caribbean Regional Group and all of the participants that we've had in these two series, we really appreciate your time and your energies, and it's been fantastic. So
Great.
If there are no other
Thank you very much.
questions, yeah, anything else that you'd like to say before we close off? Or?
No, that just thank you very much for listening and for inviting me. I'll send around a copy of the slides afterwards, so you can go back to them for further reference. But if you've got any questions or anything, then feel free just to drop me an email or yeah, get in touch. Okay, will do. And we do have recordings of these presentations, which I believe we probably load on to the IStructE website at a soon to be released date. But appreciate it, and to all of the participants, thank you as well. So do enjoy the rest of your day, wherever you're logging in from, and take care. Bye. Right. Thanks everyone. Bye.
Cheers, Tom.
Cool. Thanks for that, Shani.
You're welcome.
That's good.
I think, yeah, over the last two webinars, we've had a minimum of 50 people So I'd say on average, we had 55 people across both of them, which has been, it's been great. We
Should have
do need
practiced
to
my
do
slides a bit more.
No, I mean the carbon calculating tool, I actually used it for the first time recently, and I very quickly used it overnight because I was trying to show some carbon data on a restoration project that I did in Grenada, and just sort of how much carbon we save by not having to rebuild this new facility, right? And just by looking at beams and slabs, it was a considerable amount of carbon. So it makes a big difference. The tool is fantastic.
Hmm.
It's pretty easy to use. But thanks for telling me what the D and stuff, the little chart at the base that says A plus DC. I wasn't sure what my result was, and I wasn't sure what it meant because I was just like, I don't know how to use this data. So
Yeah,
yeah, it's no, it's been great,
cool.
and thanks so much for doing this, and we'll keep in touch.
Yeah, let's keep in touch. Yeah,
Yeah, well, probably when because you're based, you said you're not based in London, right? You're outside.
based in Manchester. Yeah,
Ah,
but
yes.
I'm down in London like once a month, so
Okay,
because
cool.
most of my team
So,
is based down in London. So
right. So whenever I'm there again, I'll probably drop you a line, and yes, let's do a meetup for coffee or a pint or something, right? So,
yeah, that sounds great.
all right,
Well
cool.
up for that.
Take care, Tom.
Great. Thanks so
Bye.
much. Thanks for inviting me. Bye.
Welcome. Take care. Bye.